Okay, children, we'll start. Sorry, I got a bit late because I had a class for grade 11s. Right, so here we are going to look at, can everyone hear me and see the screen clearly?
Yes, I can hear you.
Okay. Now this is the one which is tricky, right? I told you in binary shifts, uh, mainly it's easy, but there are some tricky parts. That's this one, arithmetic shifts. Now watch very closely and try to get the idea, right? Now we already know that logical shifts are carried out on unsigned numbers. What are unsigned numbers? These are the numbers where we don't reserve the most significant bit for the sign. If it is, if you are talking about bits or binary, we don't have the last bit right to the left side, which is the most significant bit reserved for plus or minus. In sign and magnitude, let me ask a question. In sign and magnitude method, we used the most significant bit to represent whether it is possible, positive or negative. Can you tell me what was the bit used to represent positive?
1.
Nope.
So 0?
It's 0.
Sorry.
It's the
0
other
is
way, right?
positive
Yeah.
minus negative.
Yeah. It's the other way, right? Okay. So 0 represented plus and 1 represented minus. Okay. Right. So the arithmetic shifts are carried out on signed numbers. That's the main thing, right? Logical shifts were carried out on unsigned numbers, but this one is carried out on signed numbers. Signed numbers, right? Now you know signed numbers are the are where we have a bit reserved for the sign, and also these arithmetic shifts are carried out on numbers, signed numbers, which are represented in 2's complement form. In 2's complement form. You remember there were two methods of representing negative numbers, sign and magnitude, and the 2's complement. So here we'll be dealing with sign numbers and 2's complement method. Keep that in mind. Then it's easy to do these questions. Only tricky part is filling the empty bits. Let me show you. Left arithmetic shift. Now same as before, right? If it is a left arithmetic shift, if you are moving the bits to the left, it's always going to be multiplication. Okay. Left arithmetic shift is identical to the left logical shift, except that the leftmost bit is not included because it must remain in place to indicate the sign. What does that mean? It's same as left logical shift, except that you don't do anything to the most significant bit. you don't shift the most significant bit. Why? Because this is needed to represent the sign. We don't do anything to that. Okay, so let's look at an example, right? Calculate the product of minus 36 into 2. First, keep in mind we are dealing with 2's complement values if they are negative. So this is minus 36. So we need to represent minus 36 in 2's complement form. And what do? First, we represent 36 in binary, in 8-bit binary. How do you do that? We fill the bits, right? This is 1, 2, 4, 8, 16, 32, 64, 128. How do you fill it? There's no 36 for 128, so you put 0. No 64s. 132 is there. 36 minus 32, 4 is the remainder, and you fill 1 for 4. So you have 132 and 1 4. 32 plus 4 is 36. Correct. Right. So this is 36 in 8-bit binary. 36 in 8-bit binary. Okay, what are we going to do? We are going to convert this into 2's complement. Right? So before you complete to 2's complement, you need to convert that into 1's complement. And how do you do that? By flipping the bits. So 0 becomes 1, 0 becomes 1, 1 becomes 0. So you simply flip the bits. Easy. And then finally, you convert that into 2's complement form by adding 1 to the 1's complement form, right? So they have already added, that's why they have given this answer. If you add, let me add it here, which this 1 is added, okay? Okay, now do it mentally. 1 plus 1 is 2. From 2, you keep 0 and take the carry bit to the other side. 1 plus 1 is 2. You keep 0 and take 1 there. 1 plus 0 is 1. And here it's 1, 1, 0, 1, 1. So this is the 2's complement of minus 36. Is that clear?
Yes, sir.
Okay. Now, what are we supposed to do? We have to take the minus 36 in 2's complement and perform the shift. Okay, so let me write this number again. 1, 1, 0, 1, 1, 1, 0, 0. This is minus 36 in 2's complement. Right. We had to multiply this by 2, right? In order to multiply this by 2, what are the things you had to do? You had to do a left shift. Why left shift? Because we want to multiply. Okay, now the question is, how many places we should shift? Can anyone tell me? How many places we should shift in order to multiply by 2?
So just 1, right?
Yes, excellent. That's 1 because 2 to the power 1 is 2. So I told you, right, in the previous lessons, I told you that the power value is the shift. So we are multiplying it by 2. So if you write it as a power of 2, it's 2 to the power 1. So the power value is the shift. So if I want to multiply it by 2, I need to do a left shift of 1 bit, right? So that's what you have to understand first. Okay, let's do. I'm going to put another 0 here because I'm going to move this to the left. If this is multiplied by 2, there should be 1 shift to the left with a 0 added to the right. So same as logical shift, nothing difference, nothing different, right? Leaving the most significant bit in place and shifting, oh, sorry, you don't need to add another 0 here, right? Leaving the most significant bit in place and shifting the others to the left will produce this. Okay, now this is the most important part here, right? I can't do anything to this most significant bit. Why? Because this is the sign. And you can see the sign is 1, which means this is a negative number. So in arithmetic shifts, we are dealing with sign and sign numbers. We can't shift the sign. So if I'm shifting the bits, I have to shift only these bits. That's the most important part. Okay, just a minute. Right. Okay, so that's the most important thing, right? Now when I'm shifting, this is the thing. This is the most important thing. Look, I had to move this one, right? I had to move this one to the left side. But then the question is, how, I cannot move that to the place where the most significant bit is. Then where does it go? It actually goes out. It disappears. It goes out. Okay. So this one will be gone out. And this 0 will come to this place. Okay. So remember, this 1 will be discarded because I can't move it to the most significant bit because it's intact. You can't move it. So this goes out. Is that clear? Is that
Yes,
clear?
sir.
Tisum? Rahini?
Yes, sir, clear.
Tisum?
Clear, sir.
Yeah, that's because most significant bit can't be moved, right? Okay, so this one goes out. 0 comes here, so I will write 0 here, followed by, now you don't need to move one by one, right? Just follow the pattern, right? So after 0, we have 3 ones. 1, 1, 1. After that, we have 2 zeros. Okay, I just moved one place to the left now. So there should be only one empty space. That's correct. And what do they say? The should be one shift to the left with a 0 added to the right. So for empty spaces, you have to add 0. Right. Now, what is the answer? I have to write the most significant bit or the sign bit. So the sign bit is 1. If you get confused with the sign bit, just put a square to show that it's the sign bit. Okay. Right. Followed by this pattern. This one. So that is 0, 1, 1, 1, 0, 0, 0. There you go. That's the answer. Is that what they have also given? Yes. Right. Don't forget that this the last bit or the most significant bit is the sign. So it's still a negative number and the rest is different. Okay, let's see whether this is correct. Right. What are we supposed to be getting? If minus 36 is multiplied by 2, we are supposed to get minus 72. So let's see whether this value is minus 72. Right. In a previous lesson, I told you how to check a 2's complement value. How to check whether a 2's complement value is correct. So let me write this again. 1, 0, 1, 1, 1, 0, 0, 0. And let's put the positional values. 1, 2, 4, 8, 16, 32, 64, 128. And how did I ask you to change? Check. All right. So how do you check whether this number is correct? You take the most significant bit and take that positional value as a minus value. That is minus 128. The rest, the magnitude, take it as a positive value. So what is the number we have? 32, there's 132, there's 116 and 18. 32 plus 16 is 48, plus 8 is 56. Okay, now add them up. Minus 128 plus 56. What should you be getting? 8 minus 6 is 2. 12 minus 5 is 7. And minus 72. So answer is correct. Simple. Got it? Understood? Okay. Understood? Clear?
Yes, sir.
Yeah, this you will get it only if you do it, right? You have to do it. You have to do few sums, then only you will understand it. Otherwise, it's difficult. Okay, let's look at another example before moving to the right shift. Okay. Okay, they have given only right shift now, division. Okay, let me give you this. Right. Minus, let's take minus 24 must be multiplied by 8. Minus 24 must be multiplied by 8. Okay, I'm going to do it. I'm going to show it. And you're going to give me answers, okay? Right. Tell me, if you're multiplying by 8, is it going to be okay? Now the thing is missing here. This is using sine and 2's complement. Okay, tell me, if you're multiplying, is it a left shift or right shift?
So if you're multiplying, it's a left.
It's a left shift. So do a bit of analysis like that, right? If you are multiplying by 8, how many shifts we have to do?
3.
3, good. Because 8 can be represented as a power of 2. 2 to the power of 3 is 8. So the power value is the shift. So 3 places to the left. Okay. First of all, we need to convert minus 24 to 2's complement. What is the first step? We have to represent 24 in 8 bits. Forget about the minus. Represent 24 in 8 bits. And how do you do that? 1, 2, 4, 8, 16, 32, 64. I will give you time. You also must do it. After this, I will give you 2 minutes for you to do it, right? 120. Let's put 24 into this. There's no 128, no 64s, no 32s, 116. 24 minus 16 is 8. That's 1, 8. No 4s, no 2s, no 1s. Let's check whether it is correct. There's 116 and 1, 8. 18 plus, 16 plus 8 is 24. Correct. Next is, what is next? To convert this into 1's complement. 1's complement. How do you convert into 1's complement? By,
So you're flipping.
yes, flipping the bits. Good. 1, 1, 1, 0, 0, 1, 1, 1. Now to 2's complement. To 2's complement, you have to add 1 to it. Just add 1 to it. 1 plus 1 is 2. You keep 0 and take the carry bit to the other side. 1 plus 1 is 2. Keep 0. Take the carry bit. 1 plus 1 is 2. Keep 0. Take 1. 1 plus 0 is 1. 0, 1, 1, 1. This is supposed to be minus 24 in 2's complement. This is what we are going to shift. 3 places to the left. Okay, now the shift. I'm going to write this number again. 1, 1, 1, 0, 1, 0, 0, 0. Okay, what you should not forget is that the last bit or the most significant bit is reserved. You can't move this. And it's 1, so it's a negative number and it's correct. Right, we didn't actually check whether it is correct. We can check it later on. We'll actually look at the answer and check. If the answer is correct, even 24 should be correct. No? Right, so the most significant bit is not moved. Then you have to flip, you have to shift only the other bits. And it's going to be 3 places. It's going to go 3 places to the left. Okay, now you have to be careful, right? This one will go out. What will happen to this one? This will come one place and go out. Yeah, am I right? No, right? Just a minute. Yeah, they are going to move 3 places, okay? 3 places. Now that's a bit tricky. So this is going to go out. That's you can say 1, then 2, 3. Then this one will come to this place. 1, 2, 3. And this 0 will come 1, 2, and 3. That's also going out, right? Am I right?
Yes, sir. It will be 1, 1, and then rest will be 0.
Yes, right. So it's going to be this one which will come here. And you can see rest is zeros, 0, 0. And another 0. And there are 3 empty spaces, which will be filled with zeros. All right. So the answer is supposed to be 1. That is the most significant bit, which is the sign. And then 1, 1, 0, 1, 0, 0, 0. Okay, let's check whether this number is correct, right? This is 1, 2, 4, 8, 16, 32, 64, 128. You take 128 as negative, right? Minus 128. And here, oh, I wrote it wrong, no? Sorry. All these should be zeros, no? What did I write? I wrote the other one. Zeros, right? Because these are answer, no? Right.
Yes, sir.
So here we have plus 64, right? Plus 64. So the answer should be, okay, I think we have a problem here. You know why? I took the wrong number. Because when you multiply minus 24 by 8, 8 into 4 is 32, right? 2, and then here we have 3. Then 8 into 2 is 16. And then here we have 192. 192 can't be represented with 8 bits, right? In 8 bits, the maximum is 128. So for this, I need one more bit. You understand? So my initial value is wrong. I mean, it doesn't work with 8 bits. That's why here, if you deduct, you get minus 64. You're supposed to get minus 64, but your answer is supposed to be minus 192. You see the mistake, right? Right. So let's do a small change, right? Let's get a small one, small value. So if we multiply, it should be maximum 128. It should go up to maximum 120.
So the maximum 128 is only if you are showing representing it by 8 digit.
Yeah, 8 bits. So yeah. So in the exam paper also, they should give calculations limited to 8 bits. Okay, so let me change this value. Okay, let's say okay, let's make it 10 minus 10 minus 10. Okay, can you guys do it? Minus 10 into 8. So the answer should be minus 80. Right. Give it a try.
So it should be 10110000.
Okay. Did you check the final value whether it is correct? Whether you are getting a minus 80?
Yes.
There you, right? Understood? So you can see that this number has to be within the 8 bits. Otherwise, you will have to add the extra bits. But since the book is testing only on 8-bit values, that's enough, right? Others, did you understand, Bihini? Presume, did you get the answer? So the answer is 1 0 1 0 1 1 0 0 0 0. That's the answer. If you shift the bits 3 places to the left, and the resulting value is minus 80. So what actually happened was minus 10 was multiplied by 8 after shifting 3 places to the left. Okay, understood? Tisum and Dihini?
Yes, I got the same answer.
Okay, right, great. Tisum, how about you?
Yes, got it, sir.
Brilliant. Okay, then let's move to the last one, right? Which is the right shift, right arithmetic shift. Now this is a bit tricky. Okay, here it says, when dividing signed binary numbers in 2's complement format of powers of 2, the bits are shifted to the right. That you already know. It's same as logical shift. Then this is the important thing. They are replaced at the left. Now, when you're shifting the bits to the right, empty spaces are going to be on the left side, right? And all this time, the empty spaces to the left and the right were filled with zeros when we performed the logical shift and left arithmetic shift. But when you do the right arithmetic shift, you are filling these gaps, these empty spaces, with the copies of the most significant bit. That's the thing, right? With the copies of the most significant bit. So if the most significant bit is 1, you're going to fill not zeros, but ones. That's the thing. Okay, so let's look at this example. Calculate minus 72 divided by 2 to the power 2. 2 to the power 2 means 4. So when you divide 72, when you divide 72 by 4, what is the answer going to be? Minus 72 divided by 2 to the power 2 means 4.
So minus 18.
Yes, 2 to the power 2 means 4. So it's going to be minus 18. So let's see whether we get minus 18. Okay, right. Let's do it together, all of us. Right. Again, what is the first thing we had to do? We had to represent minus 72 in 2's complement form. Minus 72. This is right arithmetic shift. Right. So minus 72 in 2's complement. What do we do first? We represent 72 in 8 bits. And you know how to do it. 1, 2, 4, 8, 16, 32. Right, okay, children. So first you write the positional values, right? 1, 2, 4, 8, 16, 32, 64, 128. Now you put 72 into this. There's no 128, that's 164. And the remaining is 8, right? And the 8 can be put here. And that's all, right? 64 plus 8 is 72. The rest will be zeros. Okay, so the next is to convert this into 1's complement. And you flip the bits. 1, 1, 1, 0, 1, 0, 1, 0. And then you convert that into 2's complement form. For that you add 1. 1 plus 1 is 0. Sorry, 2. You put 0 and take 1 there. 1 plus 1 is 2. Keep 0. Take 1. 1 plus 1 is 2. Keep 0. 1 there. 1 plus 0 is 1. Here 1, 0, 1, 0. Oh, I did a mistake. I did a terrible mistake. Okay, wait. How did I notice that I did a mistake? Because the sign bit came as 0.
So it's very wrong.
Yeah, that's the thing, right? I noticed it by looking at the sign bit. Sign bit came as 0. Then only I thought like, okay, it can't be because it's a minus negative number and I'm completely converting it to 2's complement. So in the exam also you be aware, right? That, right? So this will be 1, 1, 1, 0, 1, 1, 0, and 1. Okay, now it's correct. Sign bit is 1. Okay, now we are going to shift this. This is minus 72 in 2's complement. Okay, now we are going to do a right arithmetic shift, right? Right arithmetic shift. You're going to divide it by 4. So 4 is 2 to the power 2. Right, 2 to the power 2, 4. So tell me, how many shifts we have to do?
Shifts.
2 shifts, right? 2 shifts to the right. Okay, for this I'm going to use a point here, fraction, just to show you that these are moving to the right. Okay, now we have to do a right shift. So this 0 will, okay, this point value will be here. This 0 will come here. That's 1 and 2. This 0 will come here and then here. Okay, this 0 will come here and right here. 2 places. So this 0 comes right underneath this. And the other 2 zeros will go out of the point. Okay, now let's fill the pattern. After this 0, after this particular 0, we have 3 ones. So 1, 1, 1. And a 0. After 3 ones, we have a 0, this 0. Okay, now we have 2 empty places. And the most significant bit, which is 1. Okay, now what did the rule say? They are replaced, right? They are replaced at the left by copies of the MSB. Right now the MSB is 1. So these are going to be filled with 1s, but not zeros. If you remember, when we did the logical right shift, these were filled with zeros. But only in right arithmetic shift, right? The left empty spaces have to be filled with 1s. So this is so important, right? Okay, so our answer is going to be 1, which is the most significant bit, 2 ones, 0, 1, 1, 1, 0. Okay, let's see whether this is correct. If this is correct, we should get minus 18, right? So let's check. This is supposed to be minus 128. This we take as a positive value. And what are the positional values? 1, 2, 4, 8, 16, 32, 64, 128. Okay, what's the positive value? 64 plus 32 is 96. 96, 104, 108, 110. No, it's 110. 96, 104, 108, 110, no? 110, right? Is it? 96, 104, 108, 110. Is that correct? So now minus 128 plus 110. What's the answer? Minus 18. Our answer is correct. Understood? Is that clear?
Yes, sir.
Dihini, Tisum,
Yes, sir, clear.
Tisum.
Yes, sir. Right.
Okay, brilliant. Well done. Right. So only difference is that, right? Only difference is those empty spaces are filled with ones. Actually, copies of most significant bit. Right. So I think we have finished that. That's one small part, which is super easy. So for homework, you do these three arithmetic shifts. Divide this number by 2 to the power 2, 2 to the power 1, 2 to the power 3. Okay, then you will get a good experience. This for homework, right? You can share your homework in the common group.
Yes, sir.
Then I will check like I did.
Show that your answers are the expected results. So we should calculate it and show that we have how we calculated it, right?
Yeah, just double check to see whether our answer is correct. Your answer is correct, right?
Okay.
Just like we checked at the end, we checked whether the answer is correct. Just share it in the group, right? Don't be shy. Then I will correct and give it to you. Right. So the last part is this. This is so easy. Hexadecimal numbers. Hexadecimal means it's a number base which has 16 values. And this is mainly used in the computer. For example, you must have seen we use hexadecimal values to represent color codes. HTML color codes are represented using hexadecimal values. This is used to shrink the data, encode the data, right? So far, only 8-bit binary numbers have been considered. However, it is common for data and commands to be represented in 32 and 64 bits. It is difficult for humans to remember and manipulate 8-bit numbers, but almost impossible for 32-bit ones. So we can use a large number base like hexadecimal, which has 16 to represent lower values. Hexadecimal system uses 16 digits, which vary from 0 to 15. Now the problem is when you use 0 to 9, there's no problem. 10 and above, when we write 10, 11, 1, 12, 13, 14, and 15, this might be interpreted as 1, 0, 1, 1, 1, 2, 1, 3. To avoid that confusion, what they have done is they have given them alphabetical letters, A to F. So now the number range is from 0 to F. So you must have seen, right? Even the IPv6 version uses hexadecimal numbers. MAC address use hexadecimal numbers. Color codes use hexadecimal numbers. A common use of hexadecimal numbers is to describe colors used in computer graphics. Each of the colors have a value of 24 bits. Why 24 bits? Because we have red, green, and blue. Red, green, and blue. And for red, we use 8 bits. For green, we use 8 bits. And for blue, we use 8 bits. So 8 plus 8 plus 8, we have 24 bits. Understand? Is that clear?
Yes.
Right. Now the problem is when we want to refer to a value, color value, I can't be typing 24 bits like this. It's very difficult to deal with 24 bits to represent a color. So that's where hexadecimal comes in. Right. So hexadecimal value for this color, which is red. Right. How do you know that this is red? Because you can see only the red value is available. Right. Only the red value has all the ones, which means red is maximum. There's no green, no blue, which means this color is red, default red. And this can be represented in hexadecimal using just 3 pairs of values, hexadecimal values, right? That's FF0000. So this was possible because we used hexadecimal number. And each hexadecimal number right? Why did it shrink to this level? Because to represent a hexadecimal number, you need 4 bits, 4 binary bits, because 2 to the power of 4 is 16. So 4 of these bits can be shrinked into one hexadecimal number. And as a result, we have 3 pairs of hexadecimal numbers. Simple. Okay, now the last part is about converting hexadecimal numbers to hexadecimal numbers to denary and denary to hexadecimal, but they're doing the other way, right? Converting binary to hexadecimal and hexadecimal to binary. Okay, that's what we are going to look at now. Right, you know the importance of hexadecimal. It shrinks data, encodes data to a smaller value, so it's easy to handle. Right, so all you got to do is this. When converting binary to hexadecimal, keep in mind that we have 4 bits, right? 2 to the power 4 is 16. That means to represent hexadecimal numbers, we need 4 bits. 4 bits to represent X. Keep this in mind. So when you're converting binary to hexadecimal, just write the binary bits like this, right? And then what you do is you start from the right corner and come to the left. Start from the right and come to the left. What do? You group these bits into bits of 4. You start from the right, come to the left, while grouping them into bits of 4. 1, 2, 3, 4, divide. 1, 2, 3, 4, divide. Okay. Now having this in mind, 4 bits equals to 1 hexadecimal value, right? Now we have 2 sets of 4 bits, right? And did you know that a group of 4 bits is called a nibble? A group of 4 bits is called a nibble. A group of 8 bits is called a byte or an octet, right? That's a byte, 8 bits. A group of 4 bits is called nibble. So we have 2 nibbles here. So the first one is this and second one is this. And all you got to do is convert each 4 bits into its denary value, its denary equivalent. Okay, how do you do that? You write the positional values 1, 2, 4, 8, 1, 2, 4, 8, and then add them up, right? There's no 8s. There's 1, 4. There's 1, 2s. So 4 plus 2 is 6. There's 1, 8, 1, 4. Just like we converted those denary numbers into binary and vice versa. So there's 1, 8, 1, 4, 1, 2. 8 plus 4 is 12. 12 plus 2 is 14. 14. Now the question is, are we going to show 14 like this, or are we going to use a character? Yes, we can't represent 14 like this. 14 is E in hexadecimal. So the final answer is E6. Is that clear?
Yes, sir. So we'll have to remember what the values represent as letters, right?
Yeah, that's right. That's easy, no? See, that's easy, yeah? That's easy because, okay, let's take another
So is
example.
it like the letters in the alphabet, like the order of the alphabet?
Yeah. It's like this, Just remember 0 to 9 is the same, right? 10, 11, 12, 13, 14, 15, and start with A, B, C, D, E, and F. That's all. You just write it somewhere on the paper. Okay, let's take another example. Convert following binary to hex. 1 1 0 1 1 0 1 1 1 0. Okay, what do? You start from the right corner, go to the left, grouping them into bits of 4. 1 2 3 4. 1 2 3 4. And this one only 2, so I'm going to put 2 zeros there. Okay, then you convert these into denary equivalent. Denary equivalent. How do you convert binary to denary? You know that. You write the positional values 1 2 4 8 1 2 4 8. Now we write only up to 8. Why? Because we don't have 8 bits here. We have groups of 4 bits. And here also 1 2. Now you multiply. You don't need to do it in steps, just do it mentally, right? That's 1 8 1 4 1 2. 8 plus 4 is 2. 12 plus 2 is 14. Here we have 6. Here we have 3. Right? 3 and 6, okay. But 14, you have to use E for that. So the answer is 3, 6, E. That's the hexadecimal equivalent of this. Is that clear?
Yes,
Easy,
sir.
right? Yeah, it's super easy. Right. Then the last one is converting the hexadecimal into binary. And it's the exact opposite of this. Exact opposite. It's the reverse. So if the hexadecimal number is given like this, A6, each hexadecimal number, again, you have to keep in mind that we need 4 bits, right? We need 4 bits or a nibble to represent hexadecimal value, 1 hexadecimal value. So all you got to do is just take each of these letters and represent each using binary. So C is 12, A is 10, and represent 12 in binary, 10 in binary. Now the question is how to put these ones and zeros, right? For that, we can use that easy method, right? Remember, we filled 1 to 128 for 8 bits, but now you fill it to 1, 2, 4, 8, only 4 bits. And then put 12 into that. So for 12, there's 1, 8, 1, 4, rest is zeros. So this is 12. For 10, there's 1, 8, no 4s, 1, 2, no 1s. That's 10. Simple. So 1, 1, 1, 1, 0, 0. And then here 1, 0, 1, 0. This whole number is the binary equivalent. Understand? Clear? Understood? Is that clear? Dini, Monica, Tisum?
Yes,
Yes,
sir.
sir.
Clear.
Okay. Now you give me a value hex to binary. Let's do this as an example. You give me a hex value. Onita, give me a hex value. Onita, give me a hex value.
CD.
What?
CD.
CD. Only CD?
Yeah.
Okay, shall we take 9 also? CD 9, okay? Right. So we have three hexadecimal value, right? So we represent each hexadecimal value using binary. Simple as that. Okay. And each hexadecimal value should be represented using how many bits? How many bits? Don't forget 2 to the power 4 is 16. So we need how many bits?
So 4.
4 bits. Okay, now you write the positional values for 4 bits. 1, 2, 4, 8. Okay, let's take 9. Okay, for 9, there's 1, 8, 1, 1. There is 0. So you can write the answer 1, 0, 0, 1 for 9. That's for 9. For D, now you should know what D is, right? Okay, that of course you have to remember, or you can just write. So D is, even I forget it. Very difficult for me to remember. A, B, C, D, E, F. I used to write like this. 10, 11, 12, 13, 14, 15. Okay, so D is 13. So 13, how do you put? 1, 8, 1, 4, that's 12, and 1, 1, that's 13. Right, so 1, 1, 0, 1. C is 12. That is 1, 8, 1, 4, 2 zeros. 1, 1, 0, 0. Okay, the final answer is 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1. Now see, this long 8-bit string is represented in hex using only 3 digits. That itself shows the versatility of hexadecimal values. Understood? Did I do it right? D is 13. 13 is 8 plus 4, 12 plus 1, 13. C is 12. 8 plus 4 is 12. Yeah, right. Right, so that's the end of the chapter. Okay, so we have finished binary. I will upload the session, right? And in the next few classes, and also in the school, we'll be doing the theory chapters. Theory chapters, we are not supposed to do the complete chapter. There are few pages, few sections. I will let you know. Right? So
Okay,
you
sir.
do this also for homework, right? This one. Okay, right. See you then. Have a nice day.
Thank you, sir. Have a nice day, sir.
Okay, you too.
Bye.
Bye.